Hello everyone, in this video we are going to solve a problem finding the steady state response of the system for a given input. So we have the transfer function, which is output over input, and then we have the input. We want to find the output, the steady state response. So yt when t goes to infinity, or the steady state. So normally, before knowing the frequency response method, we change the input into Laplace, then multiply it, then use the final value theorem or initial value theorem, and find the initial or final values. But here, with the frequency method, we know if we have the input, ft here, our output would be similar to this, just the amplitude is going to change. So instead of 10, it's going to be mw times 10, so changing magnitude. And also here sine 0.2 t, 0.2, which is the frequency, would be the same, but we are going to have a change in phase as well. So our job is to find the change in magnitude and the change in phase. So I can write it here, 10 m. The change in magnitude depends on the frequency, and frequency here is 0.2. Sine 0.2 plus the change in phase at a particular frequency, which is again 0.2 here. So now I'm going to find m and phi. So let's find the change in frequency, the change in magnitude at a particular frequency. I just need to replace s with j omega. So whenever I have s, I will change it to j omega. Here I have s j omega. And then remember, j omega, omega for us is 0.2, so it's 0.2j. I'm going to replace everything with 0.2j. So if this is, the numerator is 10, it's not changing, but I have 10 times 0.2j plus 1, the whole thing, multiplied by 4, multiplied by 0.2j plus 1. If I simplify that, I will have 10, 1 plus 2j, multiplied by 1 plus 0.8j. So that was the first step, changing s to j omega, or 0.2j. Now if I want to find a magnitude, m at 0.2, the numerator is just 10, is a number. The denominator has two complex number, so I have two number multiplied, and because it's complex, I have to use Pythagorean theorem. The real part is squared plus the imaginary part is squared, so this one is squared would be 1, this one is squared would be 4. And same thing for here, I have 1 plus 0.64, that's 0.8 squared. At the end I get 3.49. So I found one change. Then the next thing would be finding the change in phase. Should be 0 minus tangent inverse of the imaginary component, which is 2 over the real component. And then I have another component or another pole here, which is 0.8. So negative 1.78. So changing magnitude and phase. And if I want to write both of them now here, my yt would be 10. I'm just rewriting this equation on the top. m.2, I have found the value is 3.49, so my magnitude or amplitude of my output is 10 times, or 3.49 times the input amplitude. And the phase is 1.78 radian different, which is a large phase change. So this is my output. So I found the output using the frequency method. while I had the frequency and the input amplitude. Now let's solve another problem. Here the transfer function is also given to us. We have the input. Now we want to find the output. So we know the output would get the form MWA, which is the amplitude, sine omega t plus VW. So what is omega? Omega is 5 here for us. So I will write M5. What is A? A is this amplitude, which is 16. Sine 5t plus the phase change. So my job is to find the change in amplitude and the change in phase. I need to find these two values. Let's just start with M5. So what do I need to do? That's the magnitude of my transfer function if instead of S I plug in j omega. What is omega for us here is 5, so I just need to replace 5j. So here if I replace it and find a magnitude, I have 2 S, let me write it here, 5j squared plus 20, 5j plus 200. J squared would be -1, and then 5 squared would be 25, so I have negative 25 here. Multiply by 2, so that would be negative 50 plus 100j plus 200. And of course the real parts can be combined, so I have 200 and negative 50, so 150 plus 100j. At the end, if I want to find m doubled m5, that would be 1 over a square root of 150, 100, and we get 0.0055. At the first glance, this seems to be a very small number, but actually the smaller it is, the more significant changes we are going to observe. Basically, the further it is from 1, that means that the amplitude is changing significantly. I still need to find a phase change, so phase change for 5, 0, tangent inverse of the imaginary component, which is 100 over 150, give me negative 0.588. If I put these together, I have 0.0055 times 16 sine 5t minus 0.588. So the value that I get would be 0.088. So my original amplitude, the input amplitude was 16, but it was changed to 0.088. So you can see there was a significant reduction in amplitude. So that small number, that means that it's multiplied by a very small number, so the amplitude changes significantly. And this is the output. So I found the output based on the input. The magnitude and the phase changed.